Hello, and welcome to C++ 11 tutorials. I'm your host James, and today we're going to talk about Rvalue references. This is the most requested feature from last time, and it's quite a big topic, actually. It's a small little thing that C++ 11 allows you to talk about, that allows you to do a couple of really big things that make a big difference to the way that you write code every day. The first one of those things is move semantics. I'm going to spend the whole of today's lesson talking about that. And next time, we will talk about perfect forwarding, which is the other thing that Rvalue references allow you to do. And let me just issue a quick warning before we begin. Move semantics and perfect forwarding are the two idioms for which you should be using Rvalue references. You shouldn't really use them outside these idioms. They have somewhat confusing behavior, and there's not really a lot you can do with them other than just make mistakes everywhere. Okay, I've written a little outline for today's tutorial, so I'm going to start off with a very quick recap of lvalues and rvalues, but otherwise I'm going to assume that you're fairly familiar with them. Then we'll talk about rvalue references. Then we'll talk about move constructors. Then std_move, the standard library function, the copy and swap idiom, and move only types. So let's begin with a very quick recap of lvalues and rvalues. So here I've declared 5 things using this somewhat barbaric syntax. However, it keeps things on one line at least. So we've got 3 expressions here which are all lvalues: x, durfp, and r of 0. Pardon me. And we've got these 3 expressions here which are rvalues: to, x plus y, and call foo. Essentially, if you're ever wondering whether an expression is an L-value or an R-value, the best approximation is whether you can take its address. So if I take the address of any 3 of these things, if I stick an ampersand in front of any of these, that makes perfect sense. Talking about the address of x makes sense, the address of durfp, and the address of r of 0. Those are all tangible things. They reside in memory somewhere. I can take their address. Whereas these 3 things, not so much. 2 is more of an abstract concept than, something that actually lives in the computer's memory. It might do, it might not. Either way, you shouldn't be taking its address. X plus y is a temporary object, so it might live in memory, it might all be optimized away, you don't know. And call foo is going to return a temporary object. And all these temporaries are destroyed at the semicolon, so they don't really have any permanent residence in memory, whatever you might think. So that's lvalues and rvalues. Now, references have existed since C++ 98. So I'm moving on to the second bit now, which is on rvalue references, which you might think is the topic of this entire video, but here I'm going to talk in some detail about what rvalue references actually are, and then later we'll talk about what they enable you to do, which is possibly more important. But we should get this, nuts and bolts stuff out of the way first. In C++ 98, I could talk about an int ref, or a ref of any type, in fact. Stick an ampersand in front of a type name, you get a reference type of that, a reference to that type. So I can say int ref rx equals x. And essentially, rx can be thought of as an alias for x. Whenever I talk about rx, I might as well be talking about x. And in fact, many compilers will optimize out rx. So for example, if I say ++rx, this could be implemented as an address, and then here there's an implicit dereferencing of that address, or the compiler might just inline this rx and just replace it with x. Either one is fine, but essentially the point is that references aren't really objects in of themselves, they're really names for things. So rx is really just another name for x. And I can talk about a const reference as well. crx equals x. These are slightly different from references, but the idea is the same. Essentially, this is a new name for x. However, this new name will not permit modification of x. So if I talk about crx, I have to be only doing reads. If I want to do writes, I have to go back to the original x. Or I could use a const cast, but those are evil. Don't use those. Cool. All right. So this is, in C++98, we would call this an int reference. However, in C++11, we revise our terminology. This is now called an lvalue reference. And it's for the very good reason that references, even back in C++98, would never bind to R values. They'd only bind to L values. So I can bind it to X, I can bind it to star P, and I can bind it to 0, R of 0. Pardon me. You can bind it to R of 0. No problem with any of those things. But I can't bind it to any of these R values. The compiler will give me an error if I try. There's a squiggle there. So when I say int ref, that's an L value reference and will only bind to L values. It will never bind to R values. Hence why we now call it an L value reference. This thing though, this const int ref, you can still call this an L value reference to const if you like, but really this is just, the term const reference is unambiguous because this thing will bind to L values and R values. I can bind it to 2, I can bind it to x plus y, and I can bind it to foo, or call foo, pardon me. Now, if I bind a const reference to an R value, something special happens, and that's called lifetime extension. Ordinarily, the object created by this R value would be destroyed at the semicolon. However, because I've bound it to a const reference, its lifetime is extended to be equal to that of the const reference, i.e. it's going to be destroyed at this curly bracket instead of at the semicolon. Okay, nothing new so far. In C++11, we now also have R value references, which you get with this double ampersand int ref. And remember how L value references would only bind to L values? Well, R value references only bind to R values. So I can say int ref rx equals 2. That's fine. Or equals x plus y. That's fine. Or equals call foo. All of these things are fine. But if I try to bind it to any of these L values, I get a compiler error. It won't happen. However, unlike this const reference that would bind to R values, I can make modifications to the temporary object with this int ref. Remember, the lifetime of the temporary is extended just like it is here to the curly brace. But unlike here, I can make modifications to this lifetime extended temporary. So, I could say plus RRX, and that's fine. Okay? There is one more kind of reference introduced, and that's a const R value reference, which you would say like this. Really, I'm just mentioning this because when there are levers for you to pull in C++, sometimes you want to pull those levers, right? But let me assure you now, there's really no reason for these references at all. Neither the move semantics nor the perfect forwarding idioms use const R value references. So, as far as I'm concerned, they have no purpose. Maybe someday someone will discover a reason for you to use them, but in anything other than very experimental code, you should not be using const R value references. So, for the rest of this episode, I'm going to pretend that they don't exist. Okay, let's move on then. So we've covered R value references. That's really all there is to it. R value references are pretty basic. They're just like L value references, except they only bind to R values. Right? Now, what they enable us to do is write move constructors. The best example I can think of for this is string. So let me include string for a sec. But vector and many of the other containers also have move constructors. Okay. So let me get rid of all this. If I have a string s, and let's say I construct it from a string literal. So this is a string. I can copy this string to another string like this, s2s. This is invoking the copy constructor for string. So s2 is an independent copy of s. It just so happens to have the same components, the same characters, but other than that, it's different. So Now, this copy construction has to go the extra mile to ensure that we actually get a copy, right? Because in order to create S2, the copy constructor has to allocate new memory, and then it has to copy over the characters from S into this new memory, and then later on, it has to destroy the memory. So we've created a lot of extra work for ourselves, but here we can reassure ourselves that that work is worthwhile, because S is still a name in the program, and S2 is a new name. We can modify those independently, so we really do need to preserve the contents of S, and the programmer is expecting value semantics here. We hasn't written pointer or reference, so the programmer is expecting a new S to exist in the program. So, ergo, we must copy S. But there are some times when this doesn't make sense. If I have a function that returns a string, like that, and then I say, oh, pardon me, then I say string S3 and construct it from make meet. Now, in C++98, the compiler is permitted to make some optimizations here. These are called the return value optimization and the named return value optimization. However, you're not guaranteed to get these optimizations, and something like 5% of the time, maybe, or maybe even 1% of the time if you're very lucky, the compiler is going to fall back to the old behavior just to ensure that the correctness of the program is not sacrificed, and it will call the copy constructor. So we have this temporary object make meet. We copy it into S3, and then we destroy the temporary. This seems like madness, does it not? Because make meet has gone away, and it's made a beautifully a beautiful slice of memory on the heap that is perfectly laid out with all the characters we want. And then rather than use that, we've just kind of copied that and then destroyed the old one, which is a lot of extra work for ourselves and kind of pointless, really, because no one would have noticed if we had just stolen the old representation and used the old resource that make meet has so kindly allocated for us. And this is where move constructors come in. So in C++11, this will never ever copy. This is always a move. Even when the return value optimization fails, you still get a move. And this is great. So it's guaranteed by the standard to work. And you might say, well, why? How does this work? How is it that this constructor knows that in this case, I definitely want to copy, and in this case, I definitely want to move? And the answer is that because we have rvalue references now, we are able to detect whether the caller used an L value or an R value using overloading. And to show you what this looks like, I'm going to go back to a type which we used in the previous episode, which is myVector. So here's myVector, and it looks pretty similar to how it did last time. It's gained a couple of new member functions. Both of these are member functions that we could have implemented in C++98. I've added this copy constructor. So the copy constructor, it does what you'd expect a copy constructor to do. It takes some other myVector and constructs a new myVector based on the elements of the old one. So we copy over the size, and then we new up a chunk of memory, and then we fill it up in this for loop. Okay? Nothing new so far, I hope. And we've added another member function called swap. Now, swap is something that we could do in C++98. Essentially, swap is sort of in the spirit of move semantics, but, well, maybe that's a topic for another day. But essentially, there's nothing weird going on in here. This is all C++98 compatible code. I take a myVector other, and I want to swap the contents of this and other. So all I do is a member-wise swap, okay? I don't need to do any heap allocation. A naive swap would look I could do a naive swap by doing something like this. I could say my vector temp and then copy construct it from other. And then I could use the assignment operator, which I haven't implemented. We'll see the assignment operator in a sec. But I could use the assignment operator to say other equals star this, and then star this equals temp. Now this is assuming that I've implemented the assignment operator, which I haven't. But you can see that this swap is actually inefficient, right? We've made this temporary here, and we've done that by calling the copy constructor. Why did we need to do that? Because this is going to go away and it's going to allocate new memory. We don't need to allocate new memory, actually. All the memory we ever need has already been allocated for us, and all we need to do is just swap some pointers and stuff. So we can get much more efficiency just by saying, okay, swap the elements pointers and swap the sizes. If you recall, my vector is just a pointer to some elements and a size. Okay? Because this is the world's simplest vector. It's nothing like stud vector, which it's like a much more simplified version of stud vector. But yeah, we can gain efficiency by doing a member-wise swap. Okay? I'm hoping that this is all, fairly straightforward. Now I want to be able to do moves, right? Just like we do with string here. So here I do a copy, here I do a move. And the way I do that is by overloading my constructor again. So here we wrote a copy constructor. And I can write another constructor that looks like this. My vector taking a my vector ref other. Now, this signature here is what we would call a move constructor. It's very similar in spirit to a copy constructor. Right? We're constructing a brand new my vector from an old one. However, our other here is taken by Rvalue reference to my vector. Therefore, in order for this parameter to bind to something at the call site, the caller must be an Rvalue. Do you remember when I said that Rvalue references will never bind to lvalues? Well, we can use that information here because in order for this overload to have been selected, the caller must be an Rvalue, and therefore, if we modify it, no one else in the program will notice. So the way that I would do this is I would say size is 0 and elements is null putter. So essentially I've initialized myself to be an empty my vector. And then I call swap with other. And that's all I need to do. So, when the move constructor is called, I initialize this to have a size of 0 and an elements null pointer. So it's an empty my vector. Then I swap with other. So in swap, we do a member-wise swap of the elements. So other's size will become 0, and my size will become the size of other. And other's elements pointer will become null, and my elements pointer will point to the memory that other had allocated for me. So essentially what we've done is we've stolen other's guts. But we've also been a little bit careful. What I could have done is just deleted all this. And then now this is quite dangerous. So I haven't initialized elements and size, so they're both just garbage, right? If you have a primitive type like int or int star and you don't initialize it, you get garbage. So that's what we have. And then we call swap. Now swap is going to give us the right stuff. So the newly constructed my vector will get the correct elements pointer and the correct size. However, other will get garbage for elements and size. And you might say, well, who cares if other's got garbage? I mean, no one's going to look at it in the program. I thought you just said that. So if other is put in an invalid state, that's fine, right? Well, there's a problem. And that's that here, I'm still using string here, but the idea is the same. After at the semicolon, the temporary object is destroyed. So this call to make meet will return a temporary object, and it's destroyed at the semicolon. And when I say destroyed, I mean the destructor runs. So whatever you do in the move constructor, you must always be wary that the destructor of the temporary object is about to run. Let's have a look at the destructor. Ooh, delete elms. Well, if others elms pointer was left as garbage, this destructor is going to wreak havoc on the program, right? It's going to be bad. We're going to delete some pointer that points to who knows. And that is really bad. That's going to bring down the program almost immediately. Or it might throw an exception if you're lucky. Well, it won't actually because it's a destructor. So this is really, really bad. So you must remember, whenever you write a move constructor, make sure you leave other in a valid state. And I've been careful to do that here by initializing myself in a valid state. You might point out in this case that I didn't need to initialize size to be 0. But I do so for safety nonetheless. Even though the destructor doesn't care what the size is, maybe something else will inspect the object in the meantime. It's unlikely, but it's good to program defensively like this. And generally speaking, the compiler will notice what you're doing, and it will say, okay, you're doing this move thing. I know what the move thing looks like. You've got this pointer assignment here that you don't need, so I'm just going to delete that, and we'll be fine. So in the end, the compiler is going to optimize it out anyway, but even though the compiler is going to do that, you must make sure that you do it right nonetheless. Because the compiler might not optimize it out, you just don't know. So you've got to be careful. Correctness is always valued over efficiency. So there you go. That's a move constructor, and it enables my vectors to be constructed efficiently from rvalues. Cool. So that's move constructors. Next, we're going to talk about stood move. So the motivation for this is maybe I as the programmer, so I as the user of a type, I have an L value of that type. Let me switch to using my vector instead of string. So if I include my vector, delete all this other stuff, even though it's great. Let's say I've got a my vector v1. And let's say it's got 1,000 elements. Maybe you think 1,000 is a lot, maybe you think it's not that many, who knows. But regardless of what you think, I definitely don't want to have to copy this, because that's ain't nobody got time for that. Now, let's say after some amount of time, I want to put it somewhere else. Let's say for whatever reason, I want to move v1 somewhere. For instance, maybe I want to move it into a brand new my vector, v2. Just for instance, okay? This is a perfectly valid thing that you might want to do. Here the example is a little bit bogus, but it motivates move fine, so don't worry. So I could type this, my vector v2 is v1. But remember that this has to go through overload resolution, this call to a constructor, just like anything else. Have a look at the overload set. So there's two constructors it could call, two viable overloads. However, this one takes an rvalue reference. And remember, rvalue references never ever bind to lvalues. They just never ever will. Never. So the compiler says, okay, there's actually one viable overload. That wins by default. The three sweetest words in the English language. So we get this overload is selected, and we get a copy. But if I know, as the user of this library, that this is the last time I'm ever going to touch v1, never going to touch it again, I can override this behavior by using the function move. So I say v2 is move of v1. Okay. Now what move is doing here, it's actually talking to the type system. Doesn't actually generate any code, doesn't do any moving at all. You can think of it as a cast. It takes v1, which is an L value, and casts it to an R value. So this expression, move of v1, is absolutely an R value. That's what it is. If you say move of some L value, you get an R value. If you say move of an R value, you still get an R value, okay? Safe to apply move to whatever you like, but essentially, when you say move of x, you're saying to the compiler, no matter what you might think, this expression, move of whatever, is an R value. And with that in mind, we can take another look at the overload set. And the compiler is going to see there's two variables. I could bind it to this one if I want to, const my vector ref other. But actually, I prefer to bind it to this one, my vector ref other. So that one's going to win. And we get a move. Great. Awesome. So that gives us a move. Now you shouldn't refer to v1 after this line. You can see now that this makes sense. It makes sense why I programmed a little bit defensively here. Imagine instead of size 0, I just deleted this, and so size got garbage. If I wasn't careful, here, if I refer to v1 again, which is super dangerous, then I could be left in trouble. Because I might actually try and access its elements, and v1 is going to, v1 is going to think that it's got a huge number of elements, or maybe even a negative number of elements, when it doesn't. So, in general, you should never ever talk about objects after they've been moved from. What you can do is you can assign to an object after it's been moved from. But in general, you want to keep usage of move to a minimum. Here it kind of makes sense. Another place where you might be tempted to use move is in a function as a return value. Let's say I have a function. I'm writing a function that returns a my vector, make vector. Maybe it takes an int. I don't know, it does something like we make a my vector, which I'm going to call ret with I elements. And then for whatever reason, we modify the I_tooth element to be minus 9,000. Don't ask me why. Now we want to get ret out of this function, right? And we want to return it by value. This is okay. In previous versions of C++, in C++ 98 in particular, you would be told never return something like a vector by value. Because imagine if I was 1,000 or even 1,000,000, something massive. Then returning by value means we have to copy that vector out. And that's expensive. However, with move semantics, we can be a bit clever here and say return move of ret. And then move will cast ret to be an R value. The move constructor is used to move ret out of this function very efficiently. So suddenly this code is okay. It's fine. And actually, we get a very nice move. And returning by value now makes a lot of sense. It's a lot cleaner than alternatives like an out parameter, for instance. Also, this usage where you say return move of ret is so common. The standard library, pardon me, not the standard library, the core language group decided, well, actually, you know what? When you've got a return statement, if you say something like return ret, even though I know ret is an L value, I can never look at ret again. Right? Ret is it's an automatic variable. It's a local variable. So I can only talk about ret inside the body of this function. So when I say return ret, even though I didn't say move, I still get a move. So you don't need to say move for a return statement. The return statement gets special treatment. But you do need to say it if you're going to do something like push it back. As an example, maybe for some reason, let me include vector for a sec. Maybe instead of make vector, you've got add vector. and this takes an int I, and it takes a vector of my vector, and we will take that by modifiable reference v, like that. Then, at the end of this function, I want to add ret into the vector. So I can say v.pushBack of ret. Now, you might expect the language to be clever here and say, oh, this is the last statement of the function, so therefore I can do a move here. But the language doesn't play any kinds of games like this. Instead, this ret is an L value, and it doesn't get special treatment like the return statement does. So it's absolutely an L value. So you need to say move here if you want to move it into the vector, like that. Cool. Alright, so that's std move. Let's talk about the copy and swap idiom. If you've been looking hard enough, you might notice, in fact I think I even mentioned it earlier, that I haven't implemented an assignment operator here. And this is quite bad because the automatically generated assignment operator is the wrong behavior in this case. So I should go away and implement one, right? Now in C++98, you probably know what an assignment operator looks like. It looks something like this. You say the type my vector ref, always returns a my vector ref, operator equals of const my vector ref other, like that. This is a C++98 assignment operator, and you should all be familiar with that signature, right? In C++11, this signature is now what we'd call a copy assignment operator, and we can we can imitate the same overloading trick we did with the copy constructor and say my vector ref. Note that this is still an lvalue reference. We never return rvalue references. Returning rvalue references is very odd, and you basically never do it. With some very well documented exceptions. Okay, so this is a move assignment operator, and you can see by doing this overloading trick, we know what's going on, right? We know that this overload will be selected for L values, this overload will be selected for R values, and then we can do the appropriate stuff in each. However, it's actually kind of annoying that we have to implement a function twice if we want to take advantage of move semantics. And for most types, it's just the copy constructor and the assignment operator that you have to imitate. But for others, maybe you want pushback, for instance, to have a move overload. It does in the standard library, for instance. There are many other examples where knowing whether or not you can steal the guts helps you write the function. Essentially, it's whenever you would normally take a copy, then you can apply this idiom, and this is called the copy and swap idiom. You can apply it to the assignment operator, and this is really cool. So instead of writing two assignment operators, one for copy assignment and one for move assignment, you write a single assignment operator that does both. And this is somewhat magical. So instead of taking by const reference in the copy assignment operator, in this unified assignment operator, we take by value. We say my vector other. This is a value. It's not a reference, it's not a pointer. This is absolutely a value. Okay? And because it's a value, I can modify it, and no one else will notice, because it's my personal value. It's nobody else's, it's mine. So I can steal its guts if I like. So in the assignment operator, what I want to do is all I need to do actually is call swap with other. Okay? Now what this is going to do, when I call swap, I am going to assume the contents of other. If you remember, this is the definition of swap. So I get other's elements pointer and I get other's size. Meanwhile, other is now going to assume my elements pointer and my size. Right? And then at this curly brace, other gets destroyed. So other's destructor runs, and it calls delete on my old elements pointer. So this is a tremendously simple implementation, and it works, right? It destroys my current elements, which is what you want from an assignment operator. You always want, if you've got a object that has a resource and you assign to it, you should always destroy that resource. And this one does so correctly by other's destructor. Okay? So this is all cool. This works. However, you might think to yourself, well, hang on a sec. I thought the whole point of this was to elide copies where possible. However, by using copy and swap, surely we are always copying. Well, names can deceive, and in fact this is not the case. Let me show you an example of the assignment operator being used. So, let's say I've got my vector v1, my vector v2, my vector v3. So I might assign to v2, maybe I do some stuff with them. Oh, pardon me, I don't have a default constructor, so I can't write this. Let me just do them with 1 and 1, for example. Or we'll use 2, doesn't really matter. Here I'm going to say v2 equals v1. So this we expect to have copy assignment. So we take v1's elements and we copy them into v2. Right? And I can also say v3 equals move of v1. And we expect this to have move assignment semantics. So v3 now assumes the contents of v1, and v1 now becomes whatever. Simple enough? But how does this work? Because we've only written one assignment operator. So how can the compiler know to give us different behavior? And the answer is that when it binds these parameters to this parameter, my vector here, my vector is taken by value, so the compiler needs to make a copy. So it looks at your constructors in order to construct. I said copy, really I meant construct. It needs to construct a new my vector into this parameter because it's taken by value. So it has a look at the constructors that are available to it. In the first case, v1 is an L value, so compiler's hands are bound. It's got to pick this copy constructor. In the second case, move of v1 is an R value. So while the compiler has a choice here, it could pick this one if it wanted. It prefers this one. So this my vector here, this parameter other, is constructed with the move constructor. And then in here we swap it. So actually, if this parameter is an R value, we don't get any copies. We move the parameter into the function, and then we do the swap. So really, even though this is called the copy and swap idiom, perhaps this should be called the construct and swap, or the move and swap. Hard to say. I quite like the sound of construct and swap, but people call it the copy and swap idiom, and you want people to know what you're talking about, so kind of stuck with that name, I guess. But that's the copy and swap idiom, which allows you to reduce code duplication by simply writing a single implementation. Okay, there's one last thing I want to talk about, and that's move-only types. This is something new that move semantics allows us to talk about. In C++ 98, we didn't know what moving was, so either your classes supported copying or they didn't. Generally speaking, classes that didn't support copying are ones that are intended to be used with inheritance and live on the heap and such. So you don't want them to be sliced. However, in C++ 11, we can talk about types that you don't want to copy and you only want to move. These are types that manage a resource, but doesn't actually make sense to copy them. And I'm going to give you an example. Let's delete a load of this code. The example I have is unique pointer. This is in the memory header. So if I say hash include memory. So unique pointer is part of the new family of smart pointers. Its cousin, shared pointer, is used when you have shared ownership, and that uses reference counting in order to make sure that the object is correctly deallocated. Unique pointer, on the other hand, assumes unique ownership, and this allows it to be much more efficient than a shared pointer. So I can say unique pointer UP and initialize it with a new int. And initialize that with, say, 1. Something like that. Oh yeah, I need to give an explicit template parameter here. So this is a unique pointer of int. Okay? That's nice. By the way, in C++14, you can use make unique instead. So you can say auto up2 is make unique of int 1. And generally this syntax is preferable because it means you don't have to say new, which is prone to be exception unsafe. However, since we're talking about C++11, I'm going to stick with this, but it's nice to point out where C++14 can be applied. Okay, so when I've got a unique pointer, I can't copy it, right? I can't say up2 of up. So I need to say the type here, unique pointer int. This is not okay. And that makes sense, right? Because the programmer has said unique pointer, so I assumed that up was going to be uniquely owned, but here you're trying to copy it. Okay, so that's bad. However, you might want to move one of these things. Imagine you have a function that returns a unique pointer. Make magic number, say. In here, I can say return unique pointer to int, and then initialize it with, say, new 12. Sorry, new int 12. And this is totally fine, because when I say return, remember that special rule before I was telling you about, where return can call the move constructor even for lvalues. However, in this case, this is an rvalue. I could even do it for lvalues, though, if I had, like, unique putter ret and then return ret. Both of these things are fine, because I'm moving the unique pointer. So when I move, unique pointer is assuming that the pointer underlying it is uniquely owned. And that's why I can't copy it, because it creates an additional owner. However, I can move it. There's nothing wrong with that, because when I move, I'm transferring ownership from one object to another. That's absolutely fine. Nothing wrong with that at all. So to show you how to implement one of these, I have made my own type called myUniquePointer, myUniquePutter here. So this is quite simple, so I'm just going to fly through it real quick. We've got the got a constructor here from an int star p, like that. The copy, we want copying to be forbidden. Now in C++98, you would do this by making the copy constructor unimplemented and private. In C++11, we can say equals delete. And this means that if anyone tries to select this function, if overload resolution results in this function, then fail to compile. So the copy constructor is still included in overload resolution, but when it is selected, fail to compile, rather than call the copy constructor. Okay? So copying is forbidden, and I've said that by using equals delete. However, moving is fine. So here's a move constructor, and I can move just fine. So I initialize myself to be null putter, and then I call swap. It's exactly the same idea as with my vector. But note that my vector also has this size to worry about. Unique pointer doesn't. It's just got this pointer here. And then the destructor calls delete, and I've got this swap, which just does a swap. And I've even given it an operator star just to make it a bit more interesting. I haven't implemented an assignment operator, but I could do that in the same way as before with something that takes by value. That's fine. Or I could just write one that takes an rvalue reference. That's also fine. Unlike in my vector, I'm not causing code duplication here because I don't need to write a copy assignment operator for move-only types. In fact, this is something that I need to do here that I've forgotten to. I need to delete the assignment operator. So my unique putter ref operator equals taking const my unique putter ref up equals delete. So I can say this in order to forbid copy assignment. However, if I just take by value here, so I do the universal one, this will fail to compile for lvalues. Why? Well, because in order to call this, I have to construct. Remember, it should be called the construct and swap idiom. So I have to construct a unique pointer. But have a look at the constructors that are available to us. The copy one is deleted, but the move one is okay. So this operator equals can't be used for an L value because we can't copy, right? The compiler will try and call this function and then fail to compile. And that's going to do it for rvalue references part 1. Tune in next time and we'll talk about perfect forwarding, which is the other idiom for rvalue references, as previously mentioned. I hope this was at least somewhat intellectual. I know that rvalue references can be a somewhat complex task. I've tried to break it down simply, and I hope that the way that it's presented here at least makes some kind of sense. The cool thing about rvalue references, though, is that they move all this complexity on the library implementation. So if you are someone who doesn't write many libraries, but maybe you use them a lot, you're going to benefit from move semantics, but you don't really need to do anything. Maybe the most you have to do is understand std move. But other than that, move semantics is just on by default. You don't have to do anything. Whenever you try and copy something using an rvalue, you're going to get a move. And that's fantastic. However, if you out there actually do need to add this to your types, then it's very important to understand how it works. And even if you don't, it's useful to understand how it works so that you can diagnose problems when they fail. Alright folks, keep it real, and hopefully I'll see you next time.